In order for you to go through this video, I would recommend that you go through the first law of thermodynamics and understand what that law is about first. Because when we go through the first law of thermodynamics, what we notice is that energy balances are being applied to whatever system is. And to be able to do that effectively, we need to have a good knowledge of the properties of the system. And that means, let's say, the pressure or the volume of the system. And then we also need to know how those properties are related to each other. So the objective of this video is to introduce the basic property relations that are relevant to thermodynamics. And in order for me to do that, I'll start off with a discussion about the state principle. But before I even move on to that, I would like to talk about the state of a closed system. So whenever we are looking at, let's say, the PV diagram or a TV diagram, where T would be representing temperature, let's say, what defines the state of a closed system? So the state of a closed system at equilibrium, let's say this is a process from 1 to 2. Okay, so this is known as the state, right? So this state of the closed system at equilibrium is its condition where it can be described by the values of its thermodynamic properties. So in terms of, let's say, it can be described in terms of this state here can be described in terms of the temperature and the volume or the specific volume of the system. Okay. And then we need to go ahead and find out uh, the number of properties that we can select as independent properties. But because if we find out the independent properties based on which this state can be defined, then for this same state, we can find out other properties based on these two properties. So for example, if, let's say, this system has these two properties as independent properties, temperature and specific volume, okay? And what we're saying is that the state principle says that all the other kind of properties, like, let's say, pressure, or could be specific internal energy, or any other intensive properties, all of these can be determined as a function of temperature and specific volume. So if I had to find out pressure, it would be of a function of temperature and specific volume. And if I had to, let's say, find out the specific internal energy of the system, again, the specific internal energy of the system is going to be a function of the temperature and specific volume of that system. So we found out that this state can actually be defined in terms of just these two properties as independent properties, and then these two properties can be used to further find out properties now that are dependent on these two independent properties. So that is what state principle is. State principle is just a guide. It's a general rule that has been developed as a guide to determine the number of independent properties that you require in order to fix the state of the system. Okay, that is what state principle is. And mostly we are talking about intensive states of the system. So just go ahead and review what that is, intensive and extensive properties. We are only going to be talking about simple compressible systems. And what this means is that we are going to be looking at pure substances like water, or maybe a uniform mixture of non-reacting gases. And these systems are classified as simple compressible systems. And why are we doing this? Because according to the experience of the scientists and researchers, we know that simple compressible systems model is useful for a really wide range of engineering problems. And for these systems, for simple compressible systems, the state principle tells us that the number of independent properties that we require, the number of independent intensive properties that we require, is 2. For example, temperature and specific volume here. So you might think here that what does the term simple here mean? So simple systems are the ones where we only have one way of letting the system energy be altered by work. Okay, so what that means is that we have two independent properties that are needed to fix the state of a simple system. And that is what we've already discussed here for simple compressible systems. And now we are going to move on, and one thing that I should again emphasize here that we are only looking at thermodynamic properties of simple compressible systems that consist of pure substances, okay? And the pure substance, you can go ahead and review what those are. They're ones that have uniform and invariable chemical composition, okay? So we're going to start off by talking about the properties of pure, simple, compressible substances, and we are going to find out the relations between properties like pressure, specific volume, and temperature. So three properties we're going to be looking at: pressure, specific volume, and temperature. Okay. And from experiments that have been performed, we know that temperature and specific volume here can be regarded as independent properties, and then pressure is determined as a function of these two, like I've already indicated here. So to combine all of these three, we have a graph that exists for all these pure substances, and the graph of all these functions is a surface, okay? So it's a surface, and it's called the PVT surface. And that is what we're going to be looking at here. The PVT surface for a substance that expands on freezing is shown here, and we're going to be discussing this in detail right now. So what you should see here, that this is a surface, okay? So this is not a volume, it's a surface. Can you imagine that when we call something a surface? For example, if I'm looking at this, let's say, cube here, the volume of this cube would indicate everything that is within this cube. But if I was to look at surfaces of this cube, the surface would be the faces of this cube. So let's say I'm looking at this surface, which is the front view of it, or I could look at this top view of it, which is another surface of this cube. So this PVT diagram, this PVT graph, is a surface, first of all. It's not a volume, it's a combination of surfaces, okay? So we're talking about substances that expand on freezing, and I would like to take a moment here, and I'll give you a few seconds to come up with an example of a substance that expands on freezing. So water is an example of a substance that expands on freezing. I hope you figured that out by yourself. So let's say we're talking about water, and if we were to look at this PVT diagram, let's say the water exists at a certain pressure and a certain temperature. So then if I was to, let's say, represent the condition of the substance of water at, let's say, this point here, this would indicate the condition of that system, and which is water. And now if I was to indicate the temperature of water at this condition, it would be somewhere here. And now to indicate the pressure, I have to look at this vertical axis. Okay, so let's say the pressure is somewhere here, and if I was to look at this axis here, this is going to be defining the specific volume of water at this condition. So let's say it's somewhere here. So these are the three axes that we're looking at when we're looking at the PVT surface: pressure, specific volume, and temperature. So one question that you might have now is that, like, let's say, what if I was to increase the pressure of water while keeping, let's say, the specific volume and temperature constant? So again, I come back to the point that this is a surface. Okay, it's not. We're not looking at this graph as a volume here. So what would happen? Let's say the specific volume here. If I was to keep this constant and temperature constant, if I was to move up my pressure, let's say from here to this point, that point would not exist for water. The water wouldn't exist at these conditions in equilibrium. That is why that point is not represented. What you can imagine is if you were looking at this graph from this side, from this perspective, if the pressure went up to this point, um, what you would have to do is go up from here vertically, okay? And that doesn't really exist because you're looking at this from this side, and this point wouldn't exist. This is not on the critical line, okay? This is actually a projection upwards. So we're looking at, let's say, if I was to show you this face, the front face, let's say this is the specific volume, this is the pressure. When you were looking at this point, it was, let's say, somewhere here. And this surface, if I was to indicate it, let's say the surface is being shown to you something like this, okay? And now, what I'm trying to say with this is that if I was to go up on my pressure value here to this point, I would have to have a projection vertically, okay? And what I see is that this point doesn't exist on the surface. It's away from the surface, okay? This point doesn't exist. Why does that not exist? Because water will not exist in an equilibrium condition at these conditions, at this specific volume, at this certain specific temperature. This pressure cannot exist. So what that means is that in order for me to, let's say, uh, fix the state of the system in terms of the specific volume and in terms of the temperature, I would get only one specific value of pressure. There cannot be a range of values at the same volume and same temperature. Okay, there's just going to be one unique pressure corresponding to the specific volume and the temperature of the system. Okay, so now let's identify the different regions that exist on this PVT surface. For, let's say, we're looking at water, so we have three different phases in which water can exist. We've got the vapor phase over here, we've got the liquid phase over here, the liquid region, and then the solid region over here. Okay, so let's just look at this liquid region first. If I was to look at this liquid region, what I see is that this is very steep. It's kind of vertical. So if I'm looking at this region, I'm talking about this region. This is the liquid region, and also you notice this dotted line here. This is behind this face, this solid face. So it's somewhere in the back, okay? It's in the back. So this is the liquid region as well, in the back of this solid region, okay? It's, if you go around this and go and look at it from this side, you will be able to see this phase of the liquid. So if I was to, let's say, have water at a certain, that exists at a certain temperature, let's say here, and it has a certain volume or a certain specific volume, and a certain pressure. Let's say I'm here at this pressure. What does this physically mean, this area? What this means is that if I was to, let's say, decrease this specific volume or increase the specific volume, if I'm decreasing the specific volume, and let's say my pressure is increasing now, it would be a sharp jump up in pressure for me. Okay. And why is that? Because water or liquids are very hard to compress. Okay, so that means uh, the rise in pressure is really steep for these kind of substances. You get this, right? Because like, what am I trying to do here? By increasing the pressure here, I'm trying to compress the liquid over here. And because this is a surface, again, I'm emphasizing this is a surface. So what that means is that if I was to, let's say, increase the pressure, sorry, the specific volume is not going to decrease that much. Okay, it's only going to change minutely. It's only going to decrease minutely, but for a minute decrease of specific volume, my pressure value is going to jump up very steeply at the same time. Okay, so let's look at this solid region now. And this solid region is even more steep than the liquid one. So what does that mean? That, and we already know that by the concept of it, by the physics behind it, by what we see physically, that solids are even more incompressible. So the specific, if I was to try and compress this solid, and what that means is that I have to increase the pressure to try and compress this solid, then I really won't be able to do much. There won't be a lot of decrease in the specific volume. Although I can keep increasing the pressure, I can keep increasing this pressure, but the solid is not going to get compressed that much. That means that the specific volume is not going to be decreased that much. So now let's look at this PVT surface and identify where the two phases exist together. So um, one of those is this liquid vapor region, right? This is um, an area on this graph where two phases, the liquid and the vapor, exist in equilibrium together. What does that mean? I'll come to that in a minute, but this line over here, it's basically cordoned off by this line here, which is called the saturated liquid line, and then this line over here, which is called the saturated vapor line, okay? And then this line here, which is called the triple line. So what is going to be happening? Let's say if I have water as a liquid over here, and if I was to try and change it into a vapor, let's say, I would have to come all the way here, get to this line, which is the saturated liquid line. Now here, only water exists as a liquid right now at this line. But as soon as I move into this two-phase region, into this liquid vapor region, now at this point, water exists not only as a liquid, but some of it also exists as a vapor. Okay, let me just indicate it by capital V. So wherever I am within the saturated liquid line, and until I get to the saturated vapor line, within this region, I would have a two-phase mixture. I would have water existing as a liquid and a vapor at equilibrium. So the more I go towards this line, towards the saturated vapor line, the more vapor is going to exist in this two-phase uh, um, basically in this two-phase region. Okay, so the more I am closer to the saturated liquid line, the more my water is going to exist as a liquid. It would still have vapor present in there. The more I move to this side, I will have more of the water existing as the vapor and lesser of it existing as a liquid, but they will be existing together in equilibrium until I reach to this point on this line. And now the water is going to exist entirely as a vapor. Okay, so this is what this represents. That this saturated liquid, it means saturation. Okay, so liquid has been saturated. It exists completely as a liquid here, and it's about to now turn into a vapor. And now the temperature is going to remain constant. The specific volume is going to start increasing. And I'm going to move across this line until I reach the vapor part of it. And now I can increase the temperature um, when the water has been completely converted into a vapor. Just going to erase this, and yeah, so this is something I already indicated. Let me just change my pen color here. So that is one of the two-phase regions that I've indicated. The second two-phase region exists between this solid and this liquid, and it's a little bit harder to look at, but it's basically this area, the area that you cannot see from the front side, but it's behind this solid region if you were to go and take a look at it from this side. Okay, so this is also indicating a two-phase region between a solid and a vapor. So if I was to, let's say, have water as a solid, as ice over here, and I was to try and increase the temperature so to convert it into a liquid, and to do that, I would have to, let's say, move from this point to somewhere along this line. And that means that this solid ice is going to be moving until it reaches this line. And then where can it move? Now the temperature cannot be increased. This is going to stay as a solid. It's going to start becoming a liquid now. So it's going to move in this direction, and it's going to start melting within this region until it reaches this line or this point. And when it reaches this point, it's converted into liquid completely. And now I can start increasing the temperature of this liquid even further, okay, to heat it up more. But within this region, when I'm converting it from a solid to a liquid where melting is taking place, the temperature is going to stay constant, okay? And then the third region, the third two-phase region that I can look at is the solid vapor region, okay? And the triple point here, this triple point, or the triple line here, sorry, this triple line indicates the line where all three of these phases, solid, liquid, and vapor, all three of them can coexist together in equilibrium at this triple line. Okay, and then another point that we can look at is this critical point, and this critical point is right at the top of this dome. This is called the vapor dome, and it's basically the point that conjoins these two saturated liquid line and saturated vapor line. Okay, and the TC here indicates the critical point temperature, or it's called the critical temperature of a pure substance. It's the maximum temperature at which the liquid and the vapor phases can coexist together at the equilibrium. At equilibrium, the pressure at this critical point is called the critical pressure, and it's indicated by P subscript C. Okay, so just like TC, we also have a critical pressure as well. And then the specific volume at this critical point is going to be indicated by V subscript C. Okay, so this is the three-dimensional PVT surface, and it really helps us in um, bringing together the relationship between pressure, between volume, between temperature, and between all the three phases of matter. Okay, and usually we, instead of working with the PVT surface, we look at the two-dimensional projections of this surface. Okay, so how can I get those projections? If I was to, let's say, look at the projection in terms of the pressure and in terms of the temperature, then I should be looking at it from this side. Okay, and then I can trace all of these from this side. And if I was to look at the pressure and specific volume, then I would have to look at this PVT surface from this side. So instead of doing that, what we do is, let's say, we take the projections onto a plane, and it's easier to do that. It's easier to work with these then. So over here we have this graph now, which gives us the relationship between pressure and volume. This is called the PV diagram. Okay, this is the PV diagram. And over here we have the relationship between the pressure and temperature of the pure substance, and this is called a phase diagram. Okay, it's called a phase diagram. And then we also have a TV diagram, which gives us the relationship between the temperature and the volume. And in the next video, we're going to be continuing on from the phase diagram and the PV diagram. And we're going to look at how we can basically come up with examples of how to use these diagrams in conjunction with using the property tables too, which are usually given at the end of your books. So for example, if you were looking at we're looking at two different books. If you're looking at Shapiro's book, Fundamentals of Engineering Thermodynamics, you would have to go all the way back to the end of the book, and you would see tables given to you. Let's say starting from table A1, and you can see the thermodynamic properties over there for pure substances. Just like that, you can also go to Cengel's book, and you would have the same thermodynamic properties to you available at the end of that book. So this is it for this video. Next video, we're going to be looking at the phase diagram, PV diagram, and TV diagram.